First of all, I would like to thank the organizers for inviting me to talk at such great conference and support. And I also thank the organizers again and staffs and graduate students for their hospitality. Thank you. So today, I'd like to talk about universal Teichmueller space. I think because this is a conference for the hyperbolic geometry and number theory, so I think many people don't familiar with the notion of universal Teichmueller space. So I will start with okay. So I should first say that this is a joint work with Dragonin Sarik, who is in the State University of New York. Okay. So okay. So now, okay. So then the first I like to, start with the definition of Kaji-conformal mapping and the universal Teichmueller space. And then secondly, I will give you the definition of the major geological laminations and boundary condition. And finally, this is the main character in this topic. In this talk is that earthquakes, which is the deformation of hyperbolic structure. And then finally, I will give you a homeomorphism theorem, which is our main theorem. So the first and second section is, I think, very elementary for the professional. So but because this is a conference for graduate students, so that I gave you a definition, elementary part, and so okay. So so many things is very elementary in the first two sections. Okay. So okay. So I will begin with Teichmueller space. What is the Teichmueller space? The Teichmueller space is the space of Kaji-conformal deformation of a fixed Riemann surface. In some sense, Teichmueller space is a space of hyperbolic structures, marked hyperbolic structure. But so in general, Teichmueller space is the deformation space of Kaji-conformal deformation space of the Riemann surface. So to explain the what is Kaji-conformal mapping, I will start with the differential Kaji-conformal mapping. Okay. So what is a differential Kaji-conformal mapping? So, but because I would like to explain what is Kaji-conformal mapping first. So I will start with what is conformal mapping. Okay. I think this is an undergraduate course of the complex analysis. No, but so I will start with this elementary part. Okay, so let F be a conformal mapping. Okay, so then the Jacobi matrix is by Cauchy-Riemann equation represented by this one. So then, because this is conformal, which is injective and holomorphic, then the derivative of is not there, so that we can take a absolute value of derivative, and then we can. So Jacobi matrix forms like this, where this part is rotation, this part is expansion, and this part is rotation. So this means that the conformal mapping sends an infinitesimal circle to the infinitesimal circle. Okay, so this is an important property of the conformal mapping. So then I will give you the definition of Kaji-conformal mapping. Okay, so let U and V be a domains, and let K be a constant greater than or equal to 1, and let small k to like this. So then, an orientation preserving diffeomorphism F U to V is said to be K Kaji-conformal mapping if this inequality hold or over any point of view. So I will explain later what is this meaning, but so this condition, when the diffeomorphism satisfies this condition, then we say that K Kaji-conformal mapping. So take an infimum of such K, then we denote by Kf and call we call this infinitum the maximal dilatation of F. So this needs need to define the topology of Teichmueller space. So recall that the conformal mapping in the case of conformal mapping, the infinitesimal picture is similarity. I mean, expansion and rotation. So what is happening in the case of Kajigono mapping? So suppose for simplicity that both of U and V contain 0 and F sent to the origin to origin. Let A and B be such partial derivatives. And then by Taylor expansion, F forms like this, where capital L is the real linear transformation, which is defined like this. So then describe the infinitesimal picture. So what happens this linear transformation? So let theta be this theta like this. I mean, A over B, B over A is, we put B over A, this one, and theta, we let theta like this. And suppose for simplicity that the A is positive. And then, by assumption, this inequity holds, and then we should notice this condition. The what happened in this case? Then the first, this part rotated minus theta, and then after then L maps circles to the ellipse. After then, so rotating like this, so that this means that L expands along the axis of angle theta and contract along the axis theta plus pi over 2. So that because of the definition, this k prime is less than or equal to k, so that and we have the ratio. We have that the ratio of the major axis and minor axis satisfies this inequity. So this means that so when you consider the K-Kaji-Kohn mapping, then the infinitesimal circle do not so deformed, right? So because we first fix capital K. So this is the condition of this is the most important condition of the K-Kaji-Kohn mapping. So okay, but this is a definition of differential Kaji-Kohn mapping. So in general, Kaji-Kohn mapping is not diffeomorphism in general, but I didn't give a definition of general definition here. So, but for instance, this map is in general sense Kaji-Kohn mapping. However, this is not diffeomorphic at the origin. But fortunately, this is a very good news that in general Kaji-Kohn mapping is differentiable almost everywhere, and our infinitesimal picture is okay at such kind of differential points. So when you encounter the Kaji-Kohn mapping in your mathematics, then you can consider the infinitesimal picture like this, and then you can be relaxed on such kind of mapping you consider like this. So property is Kaji-Kohn mapping. The first property is from the definition. I mean, if F is K Kaji-Kohn mapping, then the K prime F is also K prime Kaji-Kohn mapping for all K prime which is greater than or equal to K. And then the first property is almost trivial from the Cauchy-Riemann equation. For instance, one Kaji-Kohn mapping means conformal, the other vice versa. I mean, so because of Cauchy-Riemann equation, dy derivative, if F is conformal, then because of the Cauchy-Riemann equation, if z bar derivative is 0, this means that we can take a small k to be 0. So this means that large K is 1. And if you consider one Kajikonov mapping, then the small k is 0. So you can from the definition of this inequality, so the z bar derivative is 0, then f is holomorphic. So this is the first condition is almost trivial from the Cauchy-Riemann equation. The second condition is almost trivial from the infinitesimal picture. For instance, f is Kajikonov, then so is f inverse. So infinitesimal picture, so f expand the infinitesimal circle along the theta axis, and it contract the theta plus 2 over pi over 2 axis. So and then if you consider the f inverse, then the reverse procedure holds, so that you can see that f inverse is also K Kajikonov mapping. And then, so the third property is not so obvious, but I think this is good exercise. I mean, if you consider 1 hour after my talk, then you can understand this property. I mean, so if F1 and F2 are Kajikonov mapping, then the composition is K1 times K2 Kajikonov mapping. So then the example, this is a example which appeared before, and this is if as I said, this is not diffeomorphism at the origin, but this is if you restrict this map to the annulus, then this is diffeomorphism, and this is a K Kajikonov mapping in our sense. So proof is like this is a straightforward calculation, but this is a most important example of the Kajikonov mapping, which will appear later. And the example of non-Kajikonov mapping, I think this is one of the typical example of this with this property. I mean, so when you restrict the annulus, which is A1 over 2, so then this is a diffeomorphism from A1 over 2 to A0. But this is not Kajikonov mapping. How do you see that? I mean, this is a straightforward calculation. So because this inequality holds, but this guy tend to 1 as the absolute value of A is 10 to 1 over 2. So this we can say K Kajikonov mapping for any K. So this is an example, but we know that. So there is no Kajikonov mapping between A1 over 2 to A0. I mean, this is some kind of rigidity property of Kajikonov mapping. I mean, the word rigidity property is a keyword is this conference. So I think this is a kind of connection between the conference and my talk. Okay, I hope. Anyway, okay, so the Teichmueller space. Well, so what is a Teichmueller space? So first I define the universal Teichmueller space. And so let D be a unit disk, and let QC be the set of all Kajikonov mapping from the unit disk to unit disk. So then it is known that any Kajikonov mapping extends as a homeomorphism of the closed disk, which is coming from also the rigidity property of the Kajikonov mapping. Then the Teichmueller, so two Kajikonov mappings, this should be R, said to be Teichmueller equivalent if F is equal to composition between the A and G. I mean, where A is some automorphism. But this coincidence occurs on the boundary. So, and then the universal Teichmueller space we denote by TD is a set, a quotient space of QC over Teichmueller equivalence. So okay, so that means that the Teichmueller space is the space of Kajikawa mapping, but we only consider the boundary value. Okay, so this is called the universal Teichmueller space, and in the talk by Professor Inkan Kem, there appeared in the under Professor Oshika's talk. This appears, this function, どうしたらいいですか? Thank you. Thank you. Space of function group. So this definition will cover their talk, I guess. So anyway, so let F be a function group, and consider QC gamma be a Kajikawa mapping from D to D, which is gamma compatible. What gamma compatible means? So is which is this Kajikawa mapping with this condition. I mean, F is a Kajikawa mapping, then we consider this conjugation. Then because we see that this guy is also Kajikawa mapping, so that this should be, this is a set of, this consists of Kajikawa mapping. But we forced to be the, I mean, gamma compatibility forced to be this set contained in the automorphism. So then the function group is gamma is the quotient space of QC gamma by the Teichmueller equivalence, which is the equivalence, which is coincidence on the boundary. And it is known that this is chemically identified with the Teichmueller space of D over gamma, which is the space of marked hyperbolic structures of D over gamma. Okay, so the example. So I mentioned that this map is K-Kajikawa mapping on the plane in general sense. So consider this element, which is a Möbius transformation fixed 0 and infinity. And then by calculation, this inequality holds. This should be equal. But anyway, so the conjugation of A by W is contained in automorphism H. So we now consider the H instead of D. But anyway, so that this is equal to this is contained in the automorphism H. So this means that the map, this equivalence class is contained in the Teichmueller space of the cyclic group, of cyclic function group. So this is, I think, most important, I mean, the example of the Teichmueller space, which Teichmueller space of function group. Okay, so the topology of Teichmueller space. So this is in fact, the Teichmueller space is the complete metric space, which is defined by this inequality, which is the maximal dilatation of H, where H is taken to be the this property, Kajikawa mapping with this property. So this dt is actually complete metric on the Teichmueller space, a universal Teichmueller space, and dt is called the Teichmueller distance. And we can also Teichmueller distance on the T gamma for all function group gamma. And so with same manners. The third property is the very important property of the universal Teichmueller space. So by definition of the Teichmueller equivalence, we can have the canonical inclusion from the T gamma to TD, right? So because of Teichmueller equivalence class is defined by the equality at the boundary, so there is no restriction on the group. So that this F equivalence in the gamma is this is a well-defined map, right? So then we know that this is a continuous embedding. Actually, this is a one Lipschitz with respect to the Teichmueller matrix, but not isomorphic in general. This is proved by Otake and McMurray. And so this means that, what this means? This means that the universal Teichmueller space is the universal. I mean, the universal Teichmueller space contains all Teichmueller space. So then this is the important property of the universal Teichmueller space. Right? So next task is to define the geodesic combination. I think this also covered the Inkan Kim talk and the Professor Inkan Kim talk and Professor Oshika's talk. So so I think every person knows this slide, I guess. This is a hypermetric on the unit disk, and this is a geodesic, how behaves geodesic in the unit disk. But so we should notice that the geodesics determined by 2 points on the boundary and vice versa. Okay, so then define G be the set of all unoriented geodesics on the unit disk. That means that so this is a torus minus diagonal set over Z action. So then the G has a canonical topology inherited from the torus, and so this means that the geodesic converges D in G if and only if their endpoints converge in the torus. This means that this kind of thing is converged to this line. Why? Because this endpoint converges to these guys. So this is the topology of the set of geodesics. Okay, so so we now define the geodesic combination. So geodesic combination on D is a cross subset of unit disk which consists of disjoint complete geodesics, like this, which is consists of ideal triangles. So I think this is also some kind of keywords in this conference. Anyway. So that this behaves look like this in the space of the G, in the space G. So the stratum is of L is a geodesic combination, and either geodesics of L or component of the component of L, complement of L in D. For instance, this is a stratum, but the components are also stratum. So notice that each geodesic combination is canonically embedded into G as a cross subset, like this. This is a cross subset in this triangle. Okay, so next I should define the transverse measure. So this is the meaning of the name of measured lamination. So to let L be a geodesic combination, so for define the transverse measure, so we define some notion of homotopy preserving strata. So let two transverse arc, I1 and I2, and then, so we say that two guys homotopic in preserving strata if there is a homotopy between I1 and I2 satisfying this. The first is that I1, the zero level of this zero level of this one is sent to I1, and one level of this map is sent to I2. The second thing is that for any t, the trajectory like this is contained in a stratum. So this means that the endpoint, for instance, endpoint should contain same stratum. But moving along the trajectory, this should be contained one stratum, like this. So for instance, if you consider the intersection point with the leaf, we say this geodesic in the geodesic dimension leaf. But anyway, if you consider intersection point with leaf, then so this trajectory should be contained in the leaf. Okay, so now define transverse measure. So transverse measure mu. Okay, sorry, should be lambda. So transverse measure lambda is we support is assignment of a positive measure, random measure. Lambda, you can consider random Borel measure. But anyway, so random measure I to each closed finite hyperbolic arc I in the D, whose transverse like this. I mean, when you consider such kind of transverse arc, then for any transverse arc, you can assign the Borel measure on such kind of transverse arc. And with the invariant under the homotopy preserving strata. For instance, before I defined homotopy preserving strata, but we do not define the invariance. So that I will define later the invariance. But anyway, so the measured lamination is given by the transverse measure with support lambda. This L is said to be the support of the measure. Okay. So what is the invariance? So let I1 and I2 be a transverse arc of L, which homotopic preserving strata. The two random measure I1, I2 on I1 and I2 are invariant if this property holds. So what this meaning? Okay, so you can because this is a homotopy preserving strata between the I1 and I2, and so if you consider B in a Borel set in B in the interval, then the H of B0 is contained in the transverse arc I1. So then if you move this guy around the strata, I mean the trajectory, then you get such kind of thing. So then this condition means that if you slide along the strata, this set along strata, then the measure is invariance. Okay, so we say that the measure lamination is bounded if the Thurston earthquake norm is defined by this, where the lambda I is where I runs over all geologic arc in D within disk. But anyway, so such kind of measure is bounded. So we let MLB be the set of bounded measure lamination on D. So then we define a topology on this set later, which is compiled with the Teichmueller topology by earthquake deformations. But before defining this topology, I will give you the examples. Examples is very important, as said by Professor Neumann before yesterday. So this is a most simple example. Lamination with single geodesic. What is the transverse measure? So the transverse measure is a Dirac measure with which is a point mass of the intersection point. So why this is transverse measure? Well, if you consider the two transverse arcs, then if you think 1 hour after my talk, then you can check that this is a transverse measure. If you slide out, then these guys are coincide. So the second example is like this. This is a lamination which consists of infinite many geodesics. So this guy is also the Dirac measures. We can put the Dirac measures like this. So then this also makes a transverse measure. The third is that this is also important example is that if you consider Fuchs angle of gamma, let gamma be a simple cross geodesic on T over gamma. Then the lift of gamma is geodesic lamination with transverse measure, which is defined by the intersection number. For instance, you can consider the Dirac measure. Like so then the fourth example is I think this is not appear in the group. If you consider group, then I think you cannot appear such kind of example. But this is an also important example. Geodetic filling hyperbolic plane. I mean, so this is a many geodesics. But if you filling the like this, then so this disjoint and cross set. So this is a geodesic lamination. Okay. So the fifth example is the half the limit of the geodesic lamination is also geodesic lamination, but this is very complicated. It had to draw a picture. So the final example is that gamma invariance one. You can think of the third example, and then let gamma be a compact Fuchsian group, a measure relation gamma invariant if this invariance property holds. So that this is a Liftoff measure lamination on D over gamma, and you can define the measure lamination on this D over gamma with this property, and then every gamma invariant measure lamination is bounded. So we can think such kind of. Our notion of bounded measure lamination is not, some kind of extension of this guys. This guy. Yeah. So, okay. So earthquake. What is earthquake? So as I said, earthquake is a deformation of hyperbolic structure. So but the earthquake is defined by defined with the geologic lamination L and L. What is earthquake? Earthquake is E is a surjective map from D to D satisfying the following. The first and second property is explained later, but in detail later. But roughly speaking, that E is an isometry from when you restrict it to any stratum. And two guys, the composition of two guys are hyperbolic translation like this. So we will explain later. But anyway, so if you have an earthquake like this, then it is known that proved by Thurston that the earthquake map D is continuously extended to homomorphism on the boundary. So we know by ES1 the extension, the destruction of the extension. Okay, so we should notice that E itself does not need to be continuous, but the extension is continuous. So, okay, so let me start with the example. So the first property is this one. So E is a hyperbolic isometry when restricted to any stratum of L. So this is a very simple example. This is most simple example of the earthquake. So what this meaning? So this is not L. In this case, L is the imaginary axis. So then, so you draw a geodesic like this. Then after deforming E, it occurs like this. So there is a fault at the L, and then earthquake happens like this. So this means that this map is not continuous on the plane, but this is continuous at the boundary. Okay. So this is an earthquake. This is a fault, and this is not continuously deformed, but if you restrict at the boundary, this E is continuous. So so what is this meaning is, so in this case, the stratum consists of 3 of these guys. I mean, A and B and L. So A and B is the left part of this half plane, and B is the right part of this one, and L is the imaginary axis. And if you restrict the E to A, then this is the identity, which is an isomorphism of H. If you restrict E to L, this is also identity, which is also isomorphism, isometric on H. And if you restrict E to B, then this guy is expansion, which is also isometric in D. So this is the meaning of this property. Okay. So the next thing is as follows. So for any 2 strata, A and B, so the comparison isometry, which is the restriction isometry, is hyperbolic translation whose axis weakly separate A and B, which translate B to left as seen from A. What is meaning? Well, so this is an abstract picture. This black line is leaves of geodesic lamination. And then, so this is a strata, this is a complement of the geodesic lamination. And these four guys there. And this is some kinds of transverse arc like this. And this is some kind of horizontal line. And this black guy is on the A country. This green guy is on the B country, like this. And then earthquake happen, like this. So when earthquake happen, then A country from the black guy, green guy moves left. Okay. Okay, so like this. Black guy moves left. Okay, so first this is the before earthquake. After earthquake, green guy moves left from the black guy. So this is the meaning of the translate B to the left as seen from A. But if you are green guy, then this is a before earthquake. Then it looks strange, but the black guy also moves to left. Okay. So that this means that we can translate A to the left as seen from B. So this is the meaning of this red sentence. And so this is a missing word, weakly separate. What weakly separate means? Well, okay, so what is weakly separate? Well, so we have a restriction as comparison isometry. So then we compose this guy, then we have also isometry. But the axis of this isometry looks like this. This is a separate A and B. And this is an axis of this guy. And this axis separate A and B. So this is a meaning of weakly separate. What weakly means? So if you consider the first example, like this, then so weakly means that so this is the first example, and so the comparison isometry looks like this. When you consider A and B, then this comparison isometry is EA of Z. This means that EAZ. This means that the axis is L, and A and B is separated by axis, right? So but if you consider L instead of B, then this guy should be identity. No. If you consider L instead of A, then this should be, this also holds, but L is not separated to B by the axis. But weakly means that this guy is contained in axis. So that this is not separated, but some kind of weakly separated. So this is a definition of earthquake. Okay, so now next I move to the definition of earthquake measure. So So what is the earthquake measure? So earthquake measure is how collapse in the world. This measures how collapse in the world. So this definition as follows. So let I be a transverse arc like this. Okay, so this is a L, this is a transverse arc I. So we define measure on I. So for given n, choose a strata like this, A1 to AN. A1 is contains endpoint, AN contains also endpoint, and A1, A2 in this order. So then, so if you consider this kind of things, and then the summation of translation lengths of this guy, I mean, the translation length of comparison isometry between this one and the next one is this one, and then, so what does it mean? Well, so if you consider A1, A2, A3, A4, F, blah, 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 so then so this guy is, how this guy moves? So this guy moves like this, and this guy moves like this, so this guy moves like this. So this means that this procedure means that this summation moves to some approximation how moves from the first endpoint to the endpoint. So in each AI plus one guy moves to left from the AI guy. But this procedure continues this procedure, then the earthquake occurs like this. So then the initial endpoint, from initial endpoint, the last endpoint moves to like this. So this summation measures this, how endpoint share this kind of thing. So then this is probably a Thurston, but so if we choose these guys appropriately, so then the limit exists. I mean this measure has limits, and we define the measure on this transverse arc. So this measure defines a measure lamination. I mean transverse measure with for the L. I mean that this is a measure. This L becomes a measure lamination with this earthquake, this measure. So we call that this measure lamination lambda the earthquake measure for the E, and denoted by E lambda are earthquake map with earthquake measure lambda. So the two key results. Okay, so the first important result is proved by Thurston. So for any orientation preserving homeomorphism H on the unit circle, there is a unique measured lamination with this property. I mean this means that any homeomorphism can be represented by earthquake. Now, this is a very important result. The next result is very important for Teichmueller theory. So these two are equivalent. I mean, if H is so the first condition is that H has Kajigon-Ohmari extension on the unit disk. The second condition is that the measured lamination, or earthquake measure for H, because of Sasson result, H is represented by earthquake, so the earthquake measure is well defined for H. So earthquake measure for H is bounded. So from the two results, so there is a well-defined bijection from the Teichmueller space. This is a set of, as I said, this is a set of Kajigon mapping on the disk, of which the equivalence class, I mean the equivalence relation is defined by the coincidence at the boundary. But we can have this map, the well-defined bijection. So this map is called, we call this map the earthquake map, earthquake measure map. So then this is our main result. So okay, so what is our main result? So our main result is that when you consider there is a canonical topology on the space of bounded measure lamination, such that the earthquake measure map is a homeomorphism. Well, but in some sense, this is very trivial because you already have a bijection, so we can define topology from this bijection, right? So this is a very trivial. I mean, this seems to be trivial, but this is not interesting in my. So this is not a theorem. I mean, this is trivial. So we define the topology. So then this quotation means canonical topology on the set of bounded measure lamination, which makes this map homeomorphism. Okay, so how define the topology? So this from here, I think this is not the. This is I use many analysis, for instance, measures or something. So, okay. So please, let me. Not a weak start. I will explain later. I mean, this is very good question. Thank you very much. So this is weak start topology is weak in our sense, actually. So I will explain later. It's very, very, very good question. Thank you very much. Anyway, so that the cross ratio. So we record the cross ratio like this. So I think in the talk by Professor Newman, there cross ratio appears, but I think I don't know the coincidence, but this is some kinds of equivalence. But anyway, so cross ratio is some kinds of uniqueness. Anyway, so this is a cross ratio in our sense. And we say that a box Q is a set of all geodesic which has endpoint in the interval like this. The interval AB times CD is like this. So the set of all geodesics. But because G is the some kinds of product of the, I mean, this is some kind of a subset of torus, so that this is looks like a box in G. So on G, so there is a chemical measure called the Liouville measure, satisfying this condition. I mean, this is defined as a measure, but if you restrict the box, then this happen. I mean, this is calculated by the cross ratio. So the important property is that this is invariance property. I mean, I didn't notice that if you consider the Liouville measure and if you consider the set in G, then and gamma is automorphism of D. Then if you consider the boundary value, then the gamma act on G like this. So that in this action, so for any Borel set E, this invariance holds. So that and so what is the Liouville measure rigorously? I mean, the Liouville measure is defined like this. Like this. So how do we see this one? This is some kind of exercise, but so we know that every Möbius transformation satisfies this equality. So this equality implies this one, because we consider that this the Jacobian matrix, Jacobian of this map is nothing but this part. So then by using the invariance of, I mean the change of coordinate of integration, then we have the invariance of Liouville measure. So then, but the calculation, by calculation, this holds. And okay, set Q star be this set. I mean this is a product of this arc and this arc. And let LQ star be like this. This is like a center. And let Q be a box of with LQ is equal to log 2. I mean, we should notice that this box has Liouville measure log 2. So then by using by elementary of the complex analysis, we can see that there is a Möbius transformation D with this property. So we call this Q the center of box. LQ is the center of box. This is a map from this one. Okay. So now we are going into the deep analysis. I mean, but not deep, but some kinds of deep. Anyway, so we have we consider the Helder continuous. We consider the product distance on G. What is product distance? I mean, so because D is a Gaussian space of a torus, and the torus is a product of the S1, right? And S1 has canonical angle distance. So then the G has the product distance inherited from the angle distance. Then so this is the product distance, what I mean. So let mu be a constant like this. We said the set of Helder continuous with compact support. Let's see, Hel 0 nu, or like this. Okay, so then the nu norm of this guy is defined like this. But this is not important in this talk, but this is the definition of Helder norm. And where the bracket of the first one is the of x1 and the second one is the x and x1, y1, like this. So this means that the maximum supremum norm, I mean infinity norm of the such kind of how Helder, the constant for which measures how Helder. So let Hel 0 or Hel naught be the set of all Helder continuous function G with compact support. So then Hel 0 is nothing but the union of all of these guys. So now we say that the new test function. The new test function is the pair of phi q, where the phi is a Helder continuous function and q be a box with Liouville measure log 2. So then with this property, I mean the support is contained in q and the composition of this guy has nu norm less than or equal to 1. So then we say that the test nu is the set of all test functions. So then we next give you the definition of the Helder distribution. So what is Helder distribution? The Helder distribution is a linear functional from W on the set of all Helder continuous function with compact support with this property. I mean, for any fixed nu, this functional norm as a functional is bounded. But I mean, the supremum may depend on the Helder exponent nu in general. But let h nu be the linear functional on h0 with this boundedness condition, and then let h be the intersection of these guys. And then this is nothing but some kind of the distribution on this one. And this, I mean, this is some kind of functional on this one. So the family of mu norm makes H into a fresh space. I mean, some kinds of metric space. So then, I mean, so we should emphasize that this makes a topology on H. So okay, so I think you are very surprised because what is this going on? I mean, so I mean after then I will so I should explain first that why I define this guy. Well, so after then I will embed the set of bounded measure lamination into this H, and then we define the topology on MLB by induced topology of H. So that I mean, so I should tell you the first. I mean, for your health, I guess. I mean that you do not surprised or something. Anyway, so this is some kind of important space for us to define the define the topology on the bounded measure lamination. So the next task is how relate the bounded measure lamination to the such kind of Hilda distribution. So okay, so now we realize the bounded measure lamination as a Hilda distribution. Okay, so now because that each measure lamination lambda corresponds to a positive random measure. No. This is what I want to say. I mean, each measure lamination lambda corresponds to a positive random measure on G as follows. So for any transverse arc, so because that for any transverse arc, lambda is assigned a random measure on I, right? So with support of intersection, so then like this. So if you consider a transverse arc, then the lambda assigns the transverse measure at a random measure on I, right? So then this, if you consider intersection, so this is a space, this is a D world, but if you consider G world, these guys are dotted like this. This is a point of the G, right? This is because this is a geodesics.